Hello and welcome to Risc-V emulation in a high-level language. So after last time, I couldn't contain myself. I wanted to try out the new command line implementation. So I'm going to embark on writing a program that actually uses the command line, and it's going to be the most complex program that we've written in Risc-V assembler so far. And I'm a little precarious because I have no debugging tools available to me except very crude dumps of memory and no disassembler available yet. So it's going to be very, very slow going, but hopefully at the end we will have a working program. So let's start by jumping into our editor and let's see if we can sketch the program that we want to write in a high level language like C to guide us, because it's easy to get very lost when writing assembly language programs if you don't structure the work in, in a logical way. First thing we'll do is we'll rip out the old sample code that we have here, which is no longer needed. So what we're going to do is we're going to write the most simple, stupid program I can think of that uses the command line, which is going to be an echo program. The echo program takes its arguments and writes them back out again. So if I go to my shell, if I type echo x, back comes x. If I type echo hello world, back comes hello world. So that's the end result. That's what we want to achieve. So if I were to write this in C, the way I would do this is I would write something like this. The C program would have a char star star argv, which is the argument vector, and an arg count, which is the number of characters. And so what you would do is something like while the argument count is larger than 0, we would call the puts, actually not puts, we will call a method, we will call write, the operating system called write, and we would write to the standard output, which is file handle 1, and we would pass in the string, which is argv star argv, but we need a length of the string. So let's create a new variable called arg, which is the result of grabbing argv like this, and then writing arg and strlen of arg, like so, using the write system call. And then we also want to handle the case where if I'm not the first argument. So how do we determine that? We need to keep track of a variable. Well, okay, so we'll switch this around. We'll say for I, 0I is less than argc plus plus I. And then we check to see if I is not equal to 0, then it means that we are not the first argument, which means that previous arguments have been written, which means that we have to write a space to the screen. And sadly, we have to call a system call to write that space, and that means we have to provide it with the address of a space someplace, and that would be somewhere down here. Would have a car space, and there we would store an actual space, and then we'd pass the argument of space or the address of space as an argument to the write system call. So this will write a bunch of stuff, and then at the end we want to write a new line. Hey, there we go. And that new line is, well, let's assume that the operating system that we're running on is Windows. So we'll give it 2 bytes to write. And then here we'll have a NL equals, or this is now a string, and that is carriage return 9 feed. So this program would do the same thing as echo does, which is echo all of the command line parameters. So all we have to do now is write this inside of inside of in Risc-V assembly language. But before we do that, we notice a few things. We are calling strlen right before calling write. This one here is equivalent of calling strlen on this space, which if we make it into an actual string, would look more like that. So what it looks like, and to make our life a lot easier, is what if we were to create a function called a put string? Not the puts of the standard library, but just a happy little function. We'll call it put string like this, and it takes a single character pointer. And what we do is we say length equals strlen of pitter, and then we call write one arg with a pitter, and then the length that we just computed. So if we were to reorganize our code this way, then instead of all these raw calls to write, we can call put string on the arg, and then put string space, and finally put string new line. There we go. So all we have to do now is implement all these. Oh, and before our program terminates, of course, we need to call exit, letting the caller know that no errors occurred. So this is our program, and now we need to translate this into Risc-V assembly language. And we got to proceed carefully and slowly to make sure we don't inadvertently insert any errors. And so, oh yeah, I forgot we have to show our implementation of strlen, the function that computes the length of a null terminated string. So how does that work? Well, what we do is we say while the pointer that we're looking at not equal to 0, we just increment the pointer, and then we'll have a start. It's a copy of that original pointer, and then at the end we return pointer minus start. So this will compute the difference between the starting position of the pointer and the first position of the pointer where the pointer value is null. So this then is the program that we're going to be translating to Risc-V. Let's start doing this bottoms up. We start by translating this. Recall then that all arguments to functions are passed in registers, at least the first few ones are, and this one would be passed in register 10. So this would be x10, and this would be x10. And then we need a register to hang on to the start register. Let's use x11 as our temporary register, and then we'll just keep incrementing x10, x10, and then at the end, we subtract x10 and x11 to get the result. And that should go into x10. So here goes. We need a copy x10 into x11, and that is done with the add I instruction, where we say the target is register 11, the source is register 10, and add 0 to that x10, giving us x10 copied into x11. And then we have a loop, so we'll create a jump to the loop test, and we'll call it strlen test. And the loop test I will put down here. It will be check to see whether the byte that x10 is pointing to is 0. So we need to load the byte first of all. So we'll say load byte unsigned and store it in some scratch variable. Let's call it variable 12. Since we're not using that variable in here, we can safely stomp on that variable. And what we'll do is we'll grab the x10 register and a 0 offset of that. This reads a single byte from. Okay, so now we have that byte, and then we check to see if that byte is 0. If it is not 0, then we want to loop. So branch if not equal to 0, or branch if not equal, that 12, that register 12 that just read, we compare it to register 0, which is always 0. And then if that is not equal to 0, then we have a valid string character. So now we will go to strlen body, which is the body of the loop. And let's put the body up here. And what it will do is it will just increment x10. So we'll just use add I, that very versatile function, and we add 1 to the register 10. And then that falls down into the test again. So here is our loop. It goes from here to here, reads another byte. If it's not 0, then we go back and increment the x10 pointer, and keeps looping until we're finally done. And we find a null pointer, or sorry, not a null pointer, a null character. And at that point, we want to return in x10 the result of subtracting x10 and x11, like that. Then we have to call a return to the caller. So we call jump and link return with a special destination register of 0. We discard the return value and we pass in register 1 at offset 0. So that will take the linking register, which is register 1, and use that to return to the caller. While we're here, let's make these things, let's make them strings. So we'll say m.label space, and that is going to be a string consisting of a single space and then a terminating 0. Remember that by default the assembler will not append terminating zeros. We have to be very explicit in what we want. And then similarly for the new line, it will consist of these characters. All right, so we have the data, we have our strlen. Now let's write put string. So put string takes an argument, which as usual is going to be x10, and it first computes strlen. And now we have to manage our registers carefully. So strlen takes a pointer to a string and returns the value of that string into the length. but that is going to be in register 10 because that's how values are returned. So this will stomp over the value of x10, and we need that because in the call to write that we're doing later, we're going to need that. We're going to need that. We're going to need that register. So how do we solve this? Now we also need to make sure that right before we call write, its first parameter it expects to be 1. But we already have the length in x10. That needs to go into the third parameter, which is x12. So one thing we have to do then is say x12 gets the value of x10. So that gets that value, and now we can pass that in here. The pointer goes into x11, but Stirlang stomps on x11. So maybe we can save the initial value of x10 somewhere on the stack to avoid the problems that we're seeing with all these registers. So let's store that in the stack. Also, because we are calling a subroutine, strlen, that is going to clobber our return address, the R1 register. So we also have to save the R1 register. So there's two values that we need to save in the stack. So when we enter this function, we have to make space for those uh, uh, two variables. So we'll do this. We'll add an add-I instruction that takes the stack pointer, which is register 2, and we'll subtract 8. And this is allocate space for 2 words. And then what we do is we store a word. The first word that we store is our return address. We'll store that at the new stack pointer location offset by 0. Store return address. And then we also want to store the initial value of the string. So store initial value of the string. Okay. Pointer. Now we call strlen. So we'll say jump and link uh, strlen. That calls strlen. And now x10 will contain the length. Now we need to move that over using the add-I instruction to argument 12, or register 12, which is the third argument register. And that is done this way. Copy x10 into x12. So now that argument is completed. Now we need to retrieve the value of x10 that we stored before and put that in x11. So we'll say load word from reload the string pointer. So we're going to reload the value that we stored here is going to get reloaded here, but now into register 11. So we are golden there. And then finally we need a 1 in register 10. That's easy. And let's use the constant. Like that. Finally, no, 1. Sorry, that's the standard output handle. And then finally, we need to set the 17 register, which is the register we use to select our system caller, if you recall. That is now going to be using syscall write. And then we call ecall to dispatch to the operating system. And this is a peeve that I've been running into. Ecall doesn't take any arguments. We keep passing all these zeros. So I'm going to change ecall so that it doesn't take any arguments. And then we can change this and all the other places where ecall is called in the emulator tests. Let's change that so that it also takes no arguments. That fixes that. Okay, so now that we've written our string to the screen, we can then return to our caller, but but we need to reset our stack and our return register, R1. So we undo the damage done by strlen by restoring our link register like that. So we'll load it from the stack pointer. And then now that we have the new value, we can restore our stack pointer to the value it had when we entered the function. So we'll add that 8 back to our stack pointer. And then finally we return to our caller like that. Cool. So there's our put string function. And then finally we have our main program, which is supposed to do this mess. Okay, so argc and argv, the very important command line arguments, they're going to be passed into our function, and they're going to be passed in um, here, register 10 and register 11, arg count, arg pointer. So we can replace all the places where we say argv with x11, and argc is x10. We also need a variable I, which is the variable that we're going to be using for looping through all of our arguments. So let's use a register that we haven't used anywhere in our program. And I'm going to be doing something very unsafe here. I'm going to be using x13. Now, I don't have the Risc-V ABI memorized, but I do know that the argument registers are not guaranteed to survive a call. So if I call a function and I have a value that I care about in register 13, I'm not guaranteed that that value will survive the call. However, I know the entirety of my program, I'm not using R13 anywhere. So in this particular case, I'm allowed to do so. But it's a very unsafe endeavor that I'm doing here. But I'm trying to avoid having to write R13, the register 13 into memory and having to read it out of memory over and over again. Just to make the program a little easier to follow. Now, a compiler does all of this magic for you. It knows the ABI, it knows which registers are safe to modify, which ones are not. But for now, I'm going to make the assumption that nobody in this program is changing register 13. So what register 13 will do is it will get initialized with 0. And the way we do that is, as usual, to use add I or li, which is an alias for add I. We initialize it to 0. And then we are going to go to a function we call, or a label we call the main loop, which is the test that, the test that we're still looping inside of our arguments. You know what? Maybe we have to bite the bullet. argc and argv are currently stored in x11 and x10, and they're going to be clobbered as well. So we might as well store. Yeah, we need to store a bunch of variables. So let's do that. Let's start by adjusting our stack so that it has space for 4 variables. Make space for 4 words. And then we're going to store our words. The first one we're going to store is x10. Store argc. Store argv. And notice how we're storing them 4 bytes apart because our words are 4 bytes. And then we're going to store I, which initially will be 0. So we'll store a 0 at location 2, 8. And remember, this is register 0, but because register 0 always has the value 0, that this is the equivalent of storing a literal 0 at offset 8. So Then we also have to store a return address. So we'll store a return address at offset 12. Okay, beautiful. Now then, we've initialized I to 0, so we can immediately jump to the loop test. So I'm going to call it main test or loop test. And then in our main loop test, what we're going to do is we're going to compare the value of I with the value of argc. So we need to load argc and argv from their respective locations. So we'll say load word, and we'll load I at offset 8. So that would be register 13 is now safe. So we'll read x13 is now I, load word 10, and we load argc, argc. So if argc, if I is less than argc, then we go to the main loop. Otherwise, we're out of the loop, and now we're going to call putString and write the new line. So we're going to use the AIUPC instruction inside of register 10, and we're going to go PC rel high NL, and then M add I into register 10, the current value of register 10, and M PC rel low minus 4. This is the pattern that we have. And now we can call putString. And there's our call to putString. And then finally, we want to call the operating system and tell it that we want to exit. So we have to initialize x10. So we'll have to load a 0 into x10, and we have to load a operating system call selector into the OS emulator, exit into register 17, and then finally we call ecall, and that's the end of our program. And we don't have to worry about this. This will terminate the emulator, so we won't fall through into the putString function. So this is good. So in fact, we probably don't need to store the return address since we're just going to die. But we'll do this out of sheer politeness, I guess. Okay, so now we need to write the body of the loop. So we've finished the outer part of the loop. We're done with that. We can get rid of that now. Now we need to write the following code. So we need to get this value. So how do we do that? Well, first we need to get I. Now we've just tested I, and I is now in register 13. So we will just grab R13, but we also need argv. So we need to load argv into register. Let's load it. We don't need args. We're going to clobber R10 anyway. So we're going to use that register R10, and we're going to take argv, which is in this location. So x10 is now argv. Then we're going to add I to that pointer, but I is an integer and we need to scale it by 4 to make it an offset into that vector because the elements of argv are all 4 bytes wide. So we have to multiply um, R13 by 4. And an easy way to do that is to use the shift left logical immediate instruction and take 13 and shift it to the left by 2 bits. That is the same as multiplying I by 4. Okay, now that we have that, we now need to add those two values together, giving us x10 is now the sum of argv and I times 4. Then we fetch the pointer, which is stored in that location. So we now do load word. That fetches us the pointer. x10 is now argv of I. So now that we finally have a pointer that we can pass to putString, we'll now call putString. So and that should print the string. Now we have to reload I because I was clobbered. So we'll load the word into some scratch register, I don't know, 10, I guess. And this is get I, so I was stored here. Now we're going to get it back again, and then we're going to compare it to 0. So if it is not equal to 0, and here again, we're using register 0, which is always 0. If it's not in, then we go to a label called main skip, which will skip the printing of us. No, if it is equal to 0. If it is equal to 0, we do not wish to print a space. So we'll skip over the skip space, like that. And then we'll create the label. But if we don't skip, then we do want to put a string. So here we do the AIUPC trick again. But this time we grab the address of the variable space, which contains that single space. And then we call putString again, like that. Now, after we've printed out one of the arguments, ooh, I just realized we probably want to print that string before. Yeah, we want to do this part afterwards. Okay, so I guess we'll have to move this block of code to here. And instead of skip space, let's call this thing main right arg, just to make it a bit clearer what we're doing here. So only write space if I is not equal to 0. And as you can see, the assembly language programming depends a lot on you commenting what you're doing, because otherwise it becomes very, very hard to understand what the code is supposed to do. And so, yeah, here we go. We've printed our string. Wonderful. Now we have to test, we have to increment I and then store it into the variable, into the stack frame, because right here in the loop test, we're going to be retrieving I. So Let's do that. We're going to take I, which is in register 13, and remember, we're making a dangerous assumption that 13 is a safe register. In this program it is, but in general it will not be. It might be clobbered by any function that we might call might clobber 13. Uh, but we're going to be trusting that our program does not use register 13 anywhere. And so what we'll do now is we'll take our 13, which is the I value, and so we're going to increment it because we need to move to the next argument. And I is our argument pointer. So we add 1 to 13, move to next argument, and then we save it in R13 or in memory. So we'll take this variable here, and then we will store it. So now that we've incremented our argument, we can then fall through into the loop test where we stupidly we grab the value that we just wrote into memory and read it back into register 13. Now, I'm writing this code in a very clumsy and non-optimized way. A smarter way would be to ensure that we are using a register that is guaranteed by the operating or the calling convention to never be clobbered. Then we don't have to fool around with these save and restore calls that we're doing here. But you just want the program to work. At this point, in a future episode, maybe we will revisit this code and see if we can make it more efficient. But let's review what we've done here. So, we are leaving the stack unbalanced, but it doesn't matter because we're exiting the emulator anyway, so it doesn't matter that we unbalanced. Although, we really should make it a habit of making sure that the stack is balanced, and that we always return the return address of the caller. So let's just be strict about this. We'll put those two calls back here. This is the restore stack pointer. But before we do that, we want to load the, oops, wrong one. Load the return address like that. And then this would be the place where we would return to our caller, but all these three instructions will never be reached because this terminates execution of our program. So I'll comment them out because they won't make any difference in our program. But this is what you would typically do in any other program that doesn't exit the way this one does. So let's review our code then. We create a stack frame of 16 bytes, and we do that by subtracting 16 from the current stack pointer. And then we can now store a bunch of values into those 16 bytes. The first 4 bytes are used to store the argument count. The second 4 bytes, the argument vector, the pointer to the actual instructions. Then the I loop variable that we're using in our program, we're initializing that to 0 by storing the contents of register 0 to it, which is the same thing as a literal 0. And finally, we also store our return address, a little redundantly because we never use it, but in general, we should make an effort into keeping our stack and our return address registers correctly initialized. First thing that we do is we go to the loop test of our function, which is down here. The loop test assumes that, oh, okay, this is interesting. It assumes that register 13, no, I'm sorry, I take that back. It loads into register 13 the location of I, or the value of I, which is at location 8. Yep. So now we have an I value, and then we also need to get the argument count, which is at stack offset 0, which is looking good there. And then we compare the two, and if 13, that is I, is less than 10, that is argc, then we go to the loop body. Otherwise, if we are equal to or larger than argc, we have exhausted all of our arguments. So now we set up the x10 register to be a pointer to the NL string, which, as we saw before, was a string that contains a new line. And then we call putString to write that out to the screen. And then finally, we call the system call exit with an argument of 0 to indicate success. But if in our loop test we go back to the loop body instead, our loop body now takes the value of I, loads it from the frame. It's now in register 10, and we compare that I value with 0. If they're equal, this is the first argument. We don't want to write a space, but if it isn't the first argument, then we fall down here where we grab a pointer to the space string, and then we ask putString to write that to the screen. And then we go to the main logic, which is take the argv value, which is in stack frame offset 4. We then take our integer and multiply it by 4. Let's see, get I. Why don't we do this? We load I into register 13 instead. So now we are guaranteed that I13 is fresh. Okay, so 13, which is I, is now shifted to the left by 2. That multiplies it by 4. We then add that to the argument vector. That gives us the address of the string that we want, or a pointer to the address of the string that we want. We then fetch that pointer into register 10, and then we call putString with that value. So if everything went well, this program actually looks valid. Let's try running it. First try and see what happens. Okay. Unknown symbol putString, unknown symbol strlen. So why are we complaining about this? Because we haven't defined the labels. So label strlen and label putString. Also, notice we got this warning, watchdog timer expired. We have a watchdog timer, if you recall, that stops the emulator if it's been running for too long. We may need to bump up the limit of the number of iterations. So let's search for watchdog. And where is it? It's not in our program. What's this? Let's take a look. There it is. Okay, so let's change this to 2000. And then let's try running again. Okay, so we got one word, and then we crashed. And why did we crash? Well, it looks like our address that we're trying to read. Let's see if that address is valid. Let's see, what is bytes.length? It's 189. What's that in hexadecimal? Okay, so we're reading off the end of our code segment. Now, why would that be? And now we run into the problem that we don't really know what is going on in our program. So we have to add some debugging support. And that will take some time. and I want to stop this session here. So for the time being, we will leave our program in a broken state. We don't know exactly what the bug is. And what we'll do next time is we'll add some debugging support so that we can actually see what is going on inside of our program, and maybe we can determine the cause of the bug that I wrote. So until next time, uh, I'll see you then, and stay healthy and keep hacking.